Okay, chapter 2 is for Newton's laws of motion. Let us summarize terminologies. We consider a particle's motion. Particle has a vanishing size, so a real number can be used to identify a position of a particle if it moves along one dimension, and in case it is moving in 3 dimensions. Usually we make use of the Cartesian coordinates, that is a rectangular coordinate system, to describe the position. And position of a vector, position of a particle can be described in terms of the 3 Cartesian coordinates as a column vector, or sometimes they are expressed in terms of a linear combination of 3 components. EI hat is the ith axis of the Cartesian coordinate unit vector, and xi is the component. Once the displacement of a vector, displacement of a particle is determined, we can compute the velocity. Here, x dot is the time derivative of the displacement. That is the velocity of the particle. The acceleration of a particle is the second order time derivative of the displacement, and that is again the first order time derivative of the velocity. Next, we consider the linear momentum of a particle. Linear momentum of a particle is defined by the product of mass and velocity of that particle. Newton's laws of motion. The following 3 postulates are Newton's laws of motion. First, Newton's first law is the law of inertia. Second law is the law of force, F equals ma. And third law is action and reaction. The most important idea is the definition of the force. The definition of the force is, as shown here, time derivative of momentum. In non-relativistic theory, force can be expressed as a mass times acceleration. However, if we want to include a relativity, this mass times acceleration is not a correct definition. Instead, the first order time derivative of the linear momentum is the correct definition. In non-relativistic theory, mass does not change at all. So, if I take the derivative with respect to time for the linear momentum, the first term, m dot, vanishes. Thus, in the non-relativistic theory, mv dot is the ma, and the time derivative of linear momentum becomes ma. However, in relativity, mass of a particle is in general expressed as the rest mass m0 divided by square root 1 minus v squared over c squared, where v squared is the velocity squared, velocity of the particle squared, and c is the speed of light. Because the velocity and magnitude of the velocity of any particle is always less than the speed of light, the denominator is always less than 1. Anyway, the definition of the mass is depending on the velocity, and actually the velocity increases as it accelerates. That means m dot, this time derivative of mass, is non-zero. Therefore, we always must include this kind of factor in relativity, although this one vanishes in non-relativistic theory. So in summary, once we know what the force means, then we can begin with the first law, that is law of inertia. If F equals 0, then velocity of particle is invariant. This is the case. F equals 0 in non-relativistic theory, mass times acceleration equals 0 if there is no force. Acceleration equals 0 means velocity time derivative of velocity is 0. That means the velocity is a constant motion. Next, this is just the definition of the force. The Newton's second law is definition of the force. F is the time derivative, first order time derivative of linear momentum. Newton's third law is for the action and reaction. If we consider the interaction between the two particles, here we have identified two particles as 1 and 2, and the force applied to particle 1 by 2 is denoted by this expression. And this one represents the force on the particle 2 due to the particle 1. Newton's third law states that the force on particle 1 by 2 and the force particle on particle 2 by 1, they are the same except for the opposite direction. Therefore, we can conclude that any force by itself, suppose that we can replace this 2 by 1 prime, that is actually the same as 1. Then we substitute this expression to the original form of the Newton's third law. Then we end up with the result that F1, 2, 1 prime, that is actually F1 goes to 1. The force applied to particle 1 by itself vanishes. The Newton's third law is quite useful to find another constant motion, because any interaction between two particles cancel exactly. If we consider two particles with momenta P1 and P2 respectively, then the sum of the momentum, this momentum 1 and momentum 2, if I add these two momenta, then we find the total linear momentum of the system. Actually, particle 1 experiences force due to 2 if we consider the interaction between them only. And particle 2 experiences the net external force, that is the force applied to particle 2 by 1. And actually we know that the sum of these two forces must be the same, must be 0. The right hand side, if I add this right hand side, we end up with 0. If I add the left hand side, we find that the total linear momentum, the sum of the two momenta, has a vanishing first order time derivative. That means P1 plus P2, that is the total linear momentum, is conserved. The total linear momentum, that is P1 plus P2, if I take the time derivative, then it vanishes. So capital P is constant motion, so it is invariant. Next, we consider the law inertial reference frame. The physics law can be described in many reference frames. Reference frame, if we introduce a reference frame, then that means that we we find coordinates. For example, the simplest example of reference frame is Cartesian coordinate system. The problem is that Cartesian coordinate system itself is just mathematical. But in physics, the coordinate system, we have to describe physics law. That means, for example, if I want to write down F equals ma, I need to choose a coordinate. Sometimes it is moving, sometimes it's accelerating, and so forth. Thus, the frame of reference is quite complicated in comparison with user definition of mathematical reference frame. In physics, I choose, first of all, we choose the Cartesian coordinate system that is simplest, and all three coordinate axes are perpendicular to each other. Okay, let us consider the Cartesian coordinate system and then choose the origin. Then I can measure the displacement of a particle in such a way. And the motion of a particle is determined by time. Sometimes this pen is here, sometimes this pen is there. So only the spatial coordinates are not efficient to describe the motion of a particle. So we need four numbers: time, x, y, z components of a displacement of a particle. Next one is we need to find that whether this system, for example, the origin, is at rest or not. But in nature, we have no way to determine whether something is at rest or not, because if I choose a system of reference that is absolute, then we can determine whether it is moving with respect to that or not. But actually, there are infinite possibilities of choosing a reference frame. So in choice of inertial reference frame requires whether that coordinate system, under that coordinate system, the physics law is described well or not. We study some counterexample in the following situation. Suppose that we are in an inertial reference frame, and actually the definition of inertial reference frame is the frame is where the Newton's laws of motion are valid. So let me show what reference frame is not inertial. That means Newton's law of motion is not well described in some frame. First, we consider the free falling of an object, two objects. Two objects are falling down, but there are two different initial velocity. You can say z-axis is a vertical axis on the ground, and initially z1, the particle 1's displacement, the particle 1's displacement was h1, and particle 2's displacement was h2. Initial velocity is v0 and 0 for particle 2, and they are accelerating downward with minus g, where g is the gravitational acceleration near the surface of the Earth. From previous relation, we can compute the displacement of particle 2 measured with respect to particle 1. This z2 over 1 means z2 minus z1. That means the displacement between the relative displacement z2 with respect to z1. As we know, particle 1, both particle 1 and particle 2 are accelerating downward. In any case, the relative displacement does not have t-squared dependence at all. That is accelerating term. Because both of them accelerating with the same acceleration, minus 1/2 gt squared cancel exactly. The only surviving term is the initial height difference and the relative velocity. So, if the two particles are observed on the ground, we can observe the acceleration due to the gravitational force. However, if we measure the motion of particle 2 from particle 1, because both of them are accelerating with the gravitational acceleration g, there is no acceleration at all. That means if I make use of this reader, we find that the frame of reference fixed to the falling particle 1 does not measure any acceleration of particle 2. If I apply Newton's second law here, Newton's first law, this particle 2 is moving with constant velocity. Okay, then I conclude that there is no force at all. Am I right? No, not at all. It is actually moving, both of them are accelerating. So choosing the rest frame of particle 1, that means even though it is accelerating with respect to a people observer on the ground, to particle 1, particle 2 is moving with constant velocity, means that there is no force at all. That means if we choose a reference frame and with an accelerating frame, Newton's law is not described in such a way that F equals ma. Right? To the person fixed to the reference frame fixed to particle 1, he cannot describe in such a way that constant velocity particle does not have any force. But actually they have force. Actually, there's a deep relationship between the inertial mass and gravitational mass, and it's very close, very deeply related to the general relativity, but let me stop the discussion regarding that one. Anyway, our conclusion is that choice of reference frame is quite important, and sometimes even the physics law equation can change. But we will find that there is a certain rule to translate the theory from the theory obtained in a inertial reference frame. But for the time being, we postpone that analysis until we study the rotating frame problem in chapter 11. Okay. Number 10, these are trivial for the graduate students, so let me pass. General Galilean relativity. Galilean relativity is the relationship between two inertial reference frames. So anyway, we have decided to make use of a system that is inertial. That means the physics laws are the same. Let me check whether it is true or not. Suppose that we have a frame S that satisfies Newton's second law. And another frame, I don't know whether it satisfies the Newton's second law or not, but what I know is the relative velocity of these two origins is fixed. If I look at a particle from the frame S and frame S prime, as far as the displacement is concerned, because the displacement of O prime from O is Vt, we have a simple relation that the displacement of this particle measured in S is displacement of that particle measured in S prime, and there is a difference by Vt. Remember, we have introduced the relative velocity of the two coordinate system as v, which is a constant. If I take the first order time derivative of the displacement x, what we find is displacement of particle measured in S equals to the displacement of the particle measured into S prime plus the relative velocity. This is some kind of rule to translate the displacement and velocity of a particle. But if I take the derivative one more time, that constant piece, this relative velocity of the two coordinate system, cancel exactly. That is just zero as far as the constant velocity case. Then double time derivative of displacement is the acceleration measured in S. This guy, double time derivative of that particle, this acceleration measured in S prime. And actually this one vanishes. So acceleration in frame S and acceleration in frame S prime, they are identical to each other. Therefore, as far as we know, F equals ma is written in frame S, then F prime equals ma prime, that is a physics law written in S prime, and actually they must be the same. Why? A is identified to be A prime. So A prime, we do not have to introduce a different acceleration. It is common acceleration in both reference frames. As a result, because this guy is the same as the force defined in S prime, the force in S prime must be the same as the force in S. So force is a universal quantity in the Galilean relativity. Thus, if we measure some physical variable in a frame and you want to translate to another one, you had better to choose inertial reference frame. That means that has a constant relative velocity compared to relative to the original reference frame. If it is not the case, you have additional piece. If v is not constant, you have additional acceleration. That means that is the origin of a fictitious force. Okay, next we consider angular momentum and torque. F equals ma is the Newton's second law of motion for the linear case. That means, however, Newton's law of motion is not only for the linear motion, but also for the rotational motion. Therefore, we had better define rotational version of momentum. Linear momentum is mass times velocity, but angular momentum is a cross product of polar vector, that is the displacement from the origin of the coordinate system, and cross product of x and p. This is usually, we call it angular momentum, but in general, if we study quantum mechanics, the angular momentum is in general sum of orbital angular momentum and spin angular momentum. And this is only for the orbital angular momentum. Orbital angular momentum means it has some orbit. You can look at the motion of a particle. So orbital angular momentum requires actual motion. But spin angular momentum is independent of displacement. So spin angular momentum is just intrinsic nature of a particle. So that is different. Okay. In linear case, F equals ma is actually F equals the momentum, time derivative of momentum. And rotational version of the Newton's second law is torque equals time derivative of orbital angular momentum. Okay, so torque is x cross F. F is the external force applied to that particle. And x is identical to that x that is used for the definition of orbital angular momentum. Okay. Torque, this is a kind of torque. This is seesaw or balance. Weight 1, weight 2, and this level on R1 and R2. Then if we want to make an equilibrium, then product of W1 R1 should be the same as W2 R2. That means that this guy, right hand side, this guy gives the torque along the clockwise direction. The left hand side, this guy gives a counterclockwise torque. And if the magnitudes are the same, and actually we know that the direction are opposite, so torque cancels only if the product of these two guys and product of these two guys are the same. We recall that if I want to compute the force, we take the time derivative of linear momentum. That means in non-relativistic theory, mass does not have time derivative, and there's a mass times acceleration will be the force. In the case of orbital angular momentum, we take the time derivative of orbital angular momentum to see whether it is actually the torque. I told you this torque, so the time derivative of the angular momentum can be computed in such a way. So R cross P, time derivative. And I know x dot is velocity. But you know that x cross P, time derivative must be cross P plus x cross P dot. You know, this is x cross force, time derivative of linear momentum, that is force, x cross F. So that is the same as torque. But what happens to this first term? This is momentum, mass times velocity, but mass times velocity, velocity cross velocity. So same thing, parallel to vectors, cross product vanishes. So therefore, total time derivative of linear momentum must be the same as the torque. We summarize. X cross P, time derivative. If I take the time derivative of orbital angular momentum, m v cross v. Same thing, cross product. Same thing, cross product, equals 0. And x times ma. So x cross F, that is the torque. Let us recall why A cross A is equals 0 using Levi-Civita symbols. A cross A is cross product. So let me write down the epsilon ijk, ei hat, and aj ak. So this sum is the whole amount of left hand side. As you know, aj and ak, they are numbers. If I double, AJ, AK is actually AJ. Two numbers are commutative. So if I add these two pieces and divide it by 2, and I have an overall factor epsilon ijk. Epsilon ijk to the multiplied to the first piece is this. Epsilon ijk multiplied to the second term is epsilon ijk ei hat ak aj. Okay, as you know, ii, jj, kk, they are dummy variables. So dummy variables are always summed over. So I can replace k and j with the j and k, and there is no difference at all in the final result. So k, j, j, k, I is kept the same, k, j, j, k, I is the same. All right. Now we have the same factor aj, ak, but we have Levi-Civita symbol ikj. Ikj can be replaced with minus ijk because I have to replace exchange the position of j and k. If I substitute this one to the second term, my final result is 1/2 epsilon ijk, ajak minus ajak. So identical ones are subtracted, so the final result is 0. Is evidently 0. The torque equation can also be used to identify the total angular momentum conservation in case if we consider the central force. Central force is the force where if we consider the interaction between two particles, we can connect the line connecting the two interacting particles. And radial direction ER is actually parallel to this line. Suppose that we have a very heavy particle in here, then we can choose the reference frame fixed to this heavy particle, just like that. Then the line connecting two particles is just the line connecting the origin to the light particle. So the force, as far as the force is along this radial direction of the light particle, then what we get is, this is the central force. Force is along that radial line. What is the torque? Torque is x cross f. F is proportional to the radial direction. But as we know, the radial direction is actually obtained by dividing this x vector, displacement position vector of the light particle, by the magnitude of it. You know, the force is along the ER, and ER is proportional to x. And the torque is x cross f, so x cross x appears. Same thing, cross product, this is exactly 0. That means, according to the Newton's second law of motion, the rotational version, torque is vanishing, then time derivative, first of the time derivative orbital angular momentum vanishes, that means orbital angular momentum is a constant of motion, that is invariant. Next, we consider etude machine. As you can see in this figure, let me just skip reading the problems. Just let us solve this one directly. Our constraint, we have a constraint 2-body system, mass 1 and mass 2, M1 and M2. And the distance from the pulley is defined by x1 and x2 respectively. They are under constant gravitational field, and so the left one has m1g as a weight, right one has m2g as a weight, and there is additional force, tension. If we neglect the mass or friction of this pulley, and if we can neglect the mass of the string, and if we can assume that the string is not extensible, then sum of x1 and x2 should be a constant. Let me write it as L. The sum of x1 and x2 is fixed. The equation of motion for the left one and right one are written in such a way: m1 x1, m2 x2. Left one accelerates in this way, so I have a force m1g, tension is backward, and right hand side m2g is along the x2 direction. Remember, x1 and x2 are defined to be the distance from the pulley, and tension is both upward. We find that there are three unknowns: x1, x2, and tension. But we have three equations. Three constraints can be solved. First of all, we can make use of this constraint equation to find that sum is constant and its time derivative is always zero. So does the acceleration of x1 and x2, if I sum them up, then they also vanishes. Therefore, these two equations are coupled, and I can substitute this one in here. Then we end up with the two equations with the two unknowns, the t and x1 double dot. The final result is a sum of mass multiplied by the acceleration of x1 equals the mass difference times the gravitational acceleration. Okay, so as a result, solving this equation, we can determine the acceleration of particle 1. The acceleration of particle 1 is m1 minus m2 over m1 plus m2g. We can substitute x1 double dot in this or that expression. X2 double dot is minus x1 double dot. We can determine the tension. If I substitute m1 double dot in here, m1 is factored out, and g minus x1 double dot. And g is again factored out. That becomes in 1 minus x1 double dot over g. And then m1g, open the parenthesis, 1 minus this factor, m1 minus m2 over m1 plus m2. We can combine these two together to have a single factor. The denominator is common denominator is m1 plus m2, and over factor m1g is factored out. This guy is multiplied to 1, m1 plus m2, and minus m1 minus plus m2. Here m1 cancels and m2 is doubled. To find that, we have a 2 times m1 m2 divided by m1 plus m2 g. As you know, we have a factor, product of the two masses divided by sum of the two masses. This is the reduced mass mu of the two-body system. The tension is 2 times the reduced mass multiplied by gravitational acceleration. The reduced mass is quite useful in describing two-body system. We will return to the reduced mass when we describe a system of particles at the center of mass frame or center of momentum frame. Okay, so now we finally resolved all the problem. Acceleration of particle 1 is determined in such a way, and acceleration is particle 2, actually because m1 is larger than m2. The acceleration is downward for particle 1, and acceleration for particle 2 is going up, and their magnitudes are the same, exactly the same. Intention is determined as a 2 times reduced mass multiplied by the gravitational acceleration. Next, we consider the simple harmonic oscillator. Simple harmonic oscillator is composed of a mass and spring system. Newton's second law states that force is mass times acceleration. And then, if I consider a spring, restoring force of a spring, the force is minus kx. Here, x is the displacement from the equilibrium position, where the spring is relaxed so that it does not have any restoring force at all. If I make use of this relation, force is minus kx, and force is mass times acceleration, that is coming from this Newton's second law, the equation of motion is determined in this way. Mx double dot is minus kx. If I move the minus kx term to the left-hand side, we obtain mx double dot plus kx equals 0. Because mass of a particle is non-zero, I can divide this m out in both sides. We end up with x double dot plus k over m, x equals 0. We can define a parameter omega 0 that is the characteristic frequency of the simple harmonic oscillator. Omega 0 is the square root of k over m. Then equation of motion becomes quite compact. X double dot plus omega 0 squared, x equals 0. This is actually the second order linear differential equation. And this is right-hand side is exactly 0. It is a homogeneous equation. As you remember, as long as you can find the linearly independent solution for these homogeneous equations, then the linear combination with the arbitrary parameters of these two functions will be the general solution of this equation. Let us substitute the trial solution x equals e to the lambda t. As you know, exponential function becomes exponential again, except that it has additional factor lambda after taking the derivative. Substituting the trial solution to the equation of motion, we find the quadratic equation for lambda. That is lambda squared plus omega 0 squared factor multiplied by exponential lambda t. As we know very well, any exponential function, whether the argument is real or imaginary, or in general complex, any exponential function that cannot be 0. So we can divide this exponential lambda t, and we end up with a simple quadratic equation. This quadratic equation is called the circular equation or eigenvalue equation. And the final result for the eigenvalues lambda are plus minus I omega 0. This is the reason why we have defined the parameter omega 0 as a square root of k over m. Now we have two different parameters. In case we consider the second order linear differential equation, there are at most two linearly independent solutions for the homogeneous case. We know omega, as far as omega 0 is a non-zero, this guy does not have any double root. If omega 0 is 0, then lambda equals 0. That means it does not have, let's see. If omega 0 equals 0, then k is 0. K equals 0 means that there is no spring at all. That means acceleration is 0. That means constant motion. All right. So we neglect the trivial case of omega 0 equals 0. In that case, plus I omega 0 and minus I omega 0 cannot be the same. So this case is not double root case. The two solutions are linearly independent. Then the solution is multiplying arbitrary parameter C1 and C2. We make a linear combination to find the general solution. We know the exponential function e to the I theta is actually the sum of cosine theta and I sine theta. And e to the minus I sine theta, I theta is cosine theta minus I sine theta. Therefore, exponential I omega 0 t and exponential I omega 0 t can be consistently expressed in terms of cosine omega 0 t and sine omega 0 t. The overall factor is an undetermined arbitrary parameter, so we can arbitrarily replace with another arbitrary parameter, just alpha cosine omega 0 t plus beta sine omega 0 t will be the general solution of this simple harmonic oscillator. So what we have obtained for the general solution for the simple harmonic oscillator is x of t equals to c1 cosine omega 0 t plus c2 sine omega 0 t. The velocity of that particle can be obtained by taking the derivative. And we have cosine omega 0 t. After taking the derivative with respect to t, we have minus omega 0 sine omega 0 t. Still, we have the same factor c1 in here. The next term, c2 sine omega 0 t, is replaced with omega 0 cosine omega 0 t after taking the first order time derivative. Next, we consider how to determine these two undetermined parameters, C1 and C2. They can be determined by introducing some conditions. For example, this one is a so-called initial conditions for the differential equation. X of t is known to be like that, but at t equals 0, that means initially, the particle, the mass of the simple harmonic oscillator is placed at x0. And velocity of the mass at t equals 0 is v0. If we require these two conditions, then we can absolutely determine these two parameters. That can be done in such a way. First, substitute t equals 0 to our general solution. If I substitute t equals 0, cosine becomes 1 and sine becomes 0. Therefore, x of 0 is exactly the same as a c1. If I take the time derivative, we obtain this. If I substitute t equals 0 to the velocity expression, then sine becomes 0 and cosine becomes 1. Thus, velocity at t equals 0 is a c2 times omega 0, as it is here. The initial condition here can be applied to find that c1 equals x0 and c2 is a v0 over omega 0. The result is written in this expression. X of t, displacement is x0 cosine omega 0 t plus v0 over x omega 0 sine omega 0 t. Because the x of t displacement is completely determined, we can take the time derivative to find the velocity and acceleration. If I take the derivative, cosine becomes a minus omega 0 sine omega t. So x0 is still there, but the only difference is minus omega 0. Here, if I take the derivative, sine becomes a cosine omega t, and additional factor of omega 0 removes the denominator factor omega 0. Again, we take another time derivative to find the replacement of sine omega t with omega cosine omega t without changing the over sign. The second term, cosine omega 0 t, is replaced with minus omega 0 sine omega 0 t. As a result, we find that this guy is omega v0 over omega 0 multiplied by omega 0 squared. This guy is original factor multiplied by omega 0 squared. And both terms have negative sign. We can factor this negative sign and omega 0 squared, and remaining pieces has a single term, that is the original displacement with the time dependence. If I move this right side to the left-hand side, we end up with the original equation of motion. That is x double dot plus omega 0 squared, x equals 0. Let us consider another way of expressing the final result for the general solution for the harmonic oscillator. This one requires some trigonometric algebra. Exponential I alpha and exponential I beta, they are cosine alpha plus I sine alpha and cosine beta plus I sine beta. If I expand this to factor up, real part is composed of cosine alpha cosine beta, and I squared gives a negative sign, and sine alpha sine beta. I have i's, single i's, then I is factored out cosine alpha sine beta, sine alpha cosine beta. If I multiply two exponential functions, law of exponent gives exponential I alpha plus beta. Therefore, it should be cosine alpha plus beta plus I sine alpha plus beta. Therefore, cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Sine alpha plus beta equals cosine alpha sine alpha plus sine alpha cosine beta. Therefore, if we consider this solution, this is the sum of two sinusoidal functions. Sum of two sinusoidal functions can be combined into a single sinusoidal function. Let's see. C1 and C2 are real numbers. If I square C1 and C2 and sum them up and take the square root, then this overall factor is artificially multiplied. So we need to return to the original expression by dividing the same factor for C1 over square root something and the C2 over square root something. We notice that this factor in front of cosine and that factor in front of sine, the two factors are squared and summed is always 1. Therefore, we can make a parametrization. The C1 over square root something and C2 over square root something can be written in terms of cosine theta and sine theta. You know, sine theta squared and cosine squared sum equals always 1. So if I replace this one by cosine delta and this one by sine delta, we end up with the fact that if I take the amplitude A to be the square root C1 squared plus C2, then the displacement x of t should always be expressed in terms of A cosine omega 0 t minus delta, where if I put t equals 0, cosine argument becomes a minus delta. This delta determines the initial phase. We know that we define this C1 over something to be cosine delta, C2 over something to be sine delta. Therefore, tangent delta is sine delta over cosine delta. Sine delta over cosine delta is C2 over C1. Sine delta over cosine delta. C2 over C1. You know, C2 is here, and that is V0 over omega 0. And C1 is X0. Therefore, the initial phase delta is completely determined as delta equals to arctangent V0 over X0 omega 0. Now, because this amplitude is a square root of C1 squared plus a C2 squared, and C1 is X0 and C2 is V0 over omega 0. Amplitude A is completely determined as square root of X0 squared plus V0 squared over omega 0 squared. And delta is written here, V0 over X0 omega 0. If we make use of the result, single sinusoidal function representation for the general solution of the simple harmonic oscillator, x is written in this form. And velocity of that particle, of the mass, is first order time derivative of the displacement. So cosine is replaced with sine with additional factor minus omega 0. We can make use of these expressions to compute the kinetic energy 1/2 mv squared and potential energy 1/2 kx squared. The time-dependent contribution to this kinetic energy is 1/2 m this guy squared, omega 0 squared a squared, and sine squared omega 0 t minus delta. And the potential energy can be computed 1/2 kx squared. Kx squared is 1/2 ka squared cosine squared omega 0 t minus delta. Here we find that m omega 0 squared. The definition of the characteristic frequency of the system, omega 0 equals square root k over m, can be used to replace m omega 0 squared equals k. Therefore, the kinetic energy and potential energy, both of them has a common factor 1/2 ka squared, and one guy has a sine square omega 0 t minus delta, and the other guy has a cosine squared with the same argument. Therefore, the kinetic energy, potential energy, they can be summed to obtain the total mechanical energy. As you can see, these arguments are the same. Sine squared, cosine squared, with the same argument, we have 1. Therefore, the total mechanical energy is 1/2 ka squared. Next, we consider the root mean square of nature of the kinetic energy of potential energy. These sine squared and cosine squared, they can always be expressed as a single sinusoidal function. The result is cosine 2 alpha is cosine squared alpha minus sine squared alpha. And if I substitute cosine squared alpha to be 1 minus sine squared alpha, I would get 1 minus 2 sine squared alpha. Just replace this sine squared alpha with the 1 minus cosine squared alpha, then we would obtain 2 cosine squared alpha minus 1. Therefore, from these two expressions, what we find is sine squared alpha is 1/2 1 minus cosine 2 alpha, and cosine squared alpha is 1/2 1 plus cosine 2 alpha. This means squared sinusoidal function is always expressed as a constant plus single sinusoidal function. All right, if I take the average over alpha by a unit period or multiples of unit periods, then you will find that this oscillating factor averaged out to become 0. And both of them will contribute to the final result only by half. And actually, if you add these two guys together, this plus and minus term, they cancel exactly to arrive at the result, this trivial result, sine squared alpha plus cosine squared alpha equals 1. So time average value for sine squared and cosine squared are both 1/2. So time average value, that means integrate over a period 0 to tau, and tau is omega 2 pi over omega 0, and divide this whole amount of integral by the period. Then you will find that the sinusoidal function contribution cancels exactly in this integral, and only a factor of only the constant term 1/2 is averaged out. So sine squared and cosine squared time average should be 1/2 exactly. You remember the kinetic energy and potential energy, they were both they had a common factor 1/2 Ka squared, and one factor has a cosine squared and the other one has a sine squared. If we take the time average, then the whole amount of total kinetic energy 1/2 Ka squared is shared by this kinetic energy and potential energy in the exactly same amount. Next, we consider the damped harmonic oscillator. A damped harmonic oscillator is a harmonic oscillator in which the damping force is present. Damping force is proportional to the velocity, and the strength is determined by this positive parameter B, and there is a negative sign on it to determine that the direction of the damping force is opposite to the motion. Because the damping force is opposite to the motion, F damp, we can compute the power of F damp. Power of F damp is force times velocity. So this is minus B x dot squared. It's negative definite. That means as far as it is moving, damping force decreases the kinetic energy of the particle. So at the end of the day, it just stops. Because the direction of the damping force is opposite to the motion, it is impossible to make an acceleration to make the velocity greater than the initial condition. If we include this one to the harmonic oscillator, we have equation of motion. F equals ma, and F equals harmonic oscillator minus kx, the restoring force, and the damping force minus bx dot. So removing F and just to combine these left-hand side and right-hand side into a single piece, then we find that mx double dot plus bx dot plus kx equals 0. This is a second order linear differential equation. And the right-hand side equals 0, so it is a homogeneous second order linear differential equation. The damped harmonic oscillator can be solved in the following way. The equation of motion that we just have constructed is mx double dot plus bx dot plus kx equals 0. Let us divide these both sides with the mass m. Then the equation becomes x double dot plus b over m, but let us divide by 2 and multiply 2. So defining the beta parameter to be b over 2m plus k over mx equals 0. We remember that omega 0 is a characteristic frequency square root k over m. We find that the expression becomes x double dot plus 2 beta x dot plus omega 0 squared x equals 0. We substitute a trial solution e to the lambda t to this equation. Then second order derivative gives a lambda squared, and first order derivative will give a lambda, and omega 0 constant, omega 0 squared term exists. Because e to the lambda t is never 0, we can factor this out and divide this out both sides. Finally, we end up with the quadratic equation that lambda squared plus 2 beta lambda plus omega 0 squared equals 0. We can consider the two cases. First, the discriminant. What is the discriminant of this problem? Discriminant is beta squared, d, actually this is d prime, because of the factor of 2. So beta squared minus omega 0 squared. So if the discriminant is 0, then the quadratic equation has double root. If the discriminant is non-zero, then the solutions are two distinct solutions. Oh. This is the case when the two solutions are the same. Then we remember that the final result is lambda plus minus equals minus beta plus minus square root beta squared over omega, minus omega 0 squared. If it is a double root, this guy vanishes. That means omega beta and omega are equal. And the solution is e to the minus beta t, and double root case e to the minus beta t times t. This is the in the previous chapter we studied how to determine the second solution of a second order linear differential equation when the characteristic equation gives a double root. That was obtained by finding that the Wronskian of the two linearly independent solutions is non-zero, and the equation for Wronskian is just a first order linear differential equation. After solving that equation, we have found that the second solution is obtained in this way. So if we combine these two, the final result for the double root case is x of t, arbitrary parameter c1 plus arbitrary parameter c2 times t multiplied by exponential minus beta t. It is an exponentially decaying function. But most important problem is the underdamped system. Underdamped system is the case that omega 0 is greater than beta 0. If the omega 0 is greater than beta 0, then the solution, this lambda plus and lambda minus, is composed of real part, which is minus beta, and imaginary part. Because you remember, omega 0 is greater than beta 0, so the inside of the square root is negative. That means that this one is replaced with I times the real number. Pure imaginary. This is a pure imaginary number. So this lambda plus is minus beta plus I omega prime, and lambda minus minus beta minus I omega prime. So the trial solution e to the lambda plus and minus t is replaced with exponential minus beta t multiplied by e to the I omega prime t and e to the minus I omega prime t. Here, omega prime equals square root omega 0 squared minus beta squared. Because omega 0 squared and beta squared are real, the real and positive number, omega prime must be smaller than omega 0. That means the angular frequency decreases. That means its period increases in comparison with the case of beta equals 0. Beta equals 0 is the damping force, damping parameter. If damping is present, then the frequency decreases and the period increases for the sinusoidal function.